Mm. Mm.
Okay, so last time we were discussing. Okay, so we saw how CDCL based SAT solving algorithm made improvements that it had over the basic DPLL. And one of the two most prominent improvements, the other ones are two that we were discussing, was this learning from conflicts, about some clauses that could block future such conflicts. And that is done by learning the conflict clause that is able to block a root cause for that conflict and adding that as a new origin set of clauses and non-chronological backtracking. Okay, instead of backtracking to the latest level, skip levels to backtrack to earlier level. And that is also determined by the conflict clause that you generate. So what I want to do today is go a little bit deeper. So into how, just to give you an idea of how the conflict clauses are generated, what kind of information we need to keep track as you generate the decision tree and as you simulate the algorithm, and how you could, just to give you an idea of how you can derive possible conflict clauses. And then move on to extending DPLL to work in the presence of theories. And hope I can do that. I mean, my slides has a lot more information. These slides I've used in earlier classes where I have spent more time in describing these things. At least this time, at the first level, I want to go through these things quickly and quickly get to the simplex algorithm so that Madhukar can discuss the ReLUplex, the specialized version of simplex, which is what we will be using mostly for doing the DNN verification. And once that is important for you to get started maybe on your project. And later, I revisit some of these topics that I have touched upon. Have time. Okay. So use this slide. Start. These things were done. So what I want to start with is simulating this on an example, on the same example that we saw. I don't know if you had a chance to go through some of these slides. Okay, did you? Yeah. Or I mean, anyway, I will go through them. So this is simulating this CDCL with conflict analysis and the generation of the thing. Except that now I show you, we need to maintain some additional information about what goes on inside BCP. Okay, as it generates all these, propagates these unit literals, and get some dependencies, to keep track of some dependency among the decisions that get made during the BCP process. Okay, and so that is what will be used to analyze the conflict and then generate a conflict clause that can block one of the root causes of causing the conflict. Okay, so here it's the same example. So you first start making the decision. So I'll go through this. So, and yes, the state of these, as we make decisions and you do invoke BCP, the state of the clauses change. Okay, so here the green are explicit decisions made, and red in a literal with the red thing means that reduces to 0 in that clause. So then you make X7, a decision on X7. Okay, and this will start a whole chain of BCP, generating unit clauses, and that generation and the dependency among the implied unit literals that are generated is what is kept track of this thing, that the graph that we built is called an implication graph. Okay? As a result of this decision at level 3, when that is plugged into clause 5, that makes it a unit clause. Okay, and so that unit literal is said to be implied by this decision in via the clause C5. Okay, so this is the unit clause that is derived. Then the same decision, along with an earlier decision at level 2, when plugged into C6, will result in another unit literal. Okay, and that is X6. So the implication graph, it not only keeps track of all the literals that are implied literals that are generated as a result of by the BCP process, and also the dependency among these implied literals and the clause. Okay, so every node is either an explicit decision or a literal that is implied by the BCP, and an edge with a label of a clause indicates the clause and these decisions that resulted in the generation of that literal. Okay, so for example, here X6, not of X6 is generated at 3 because of these two decisions that are made inside the clause C6, and that's how you keep generating these. Keep track of the generation of unit literals. Okay. And finally, you will then, when X2 not X3 and the decision made earlier at X1 are plugged in the clause C2, that generates the conflict. Okay. So once you have this graph, okay, so questions about this implication graph? I mean, later slides had formal definitions of these things, and at this time I may not go through those slides that give the formal definition of this graph. Any questions on this graph? Okay, the way it is generated, is it clear?
Sir, like, could you, so, uh, like, it is generated by you go through clauses
Yeah,
and,
you generate it as you as you propagate the clauses. Okay, so let me ask this question. So once you make this decision at level 3 of not X710, what does BCP do? As I told you, doing a unit resolution is like plugging the truth value that you're
yeah,
assigned.
plugging values inside it.
So
Yeah.
that's what that makes C5 unit. Okay.
Okay.
Therefore, that implies a decision on X5.
Okay.
It's that dependency and the clause that generates that implied decision is what kept track of in this
So
CPD.
this is like, yeah, if X7 is not, then like X, then we have not X5.
Yeah, so that's an implied decision. No, as a result
Oh,
of making the explicit decision of X7, C5 became unit. Yeah.
so this will all be like a DAG all around, like direct
Yes,
acyclic
that's
graph.
correct.
Okay.
Yes, this will be a directed acyclic graph.
And sir, what are those add 3, add 2, like those?
That's just the level, okay? Just to keep track, because the non-chronological backtracking, it depends on those things. I'm also keeping track. This implication graph keeps track of the decision, the level at which these decisions are made. Okay.
Oh, okay.
So I'm already assumed, yeah. So we started with level 1, okay. Although in this algorithm it starts with 0, okay.
Okay.
So except for the difference, so X1 that's the first level of decision, okay. That did not it simplified some of the clauses, but it did not generate any unit clauses, and that's why nothing is shown in the implication graph. So is after a decision on X8 is made. That's level, okay? That's showing the level. I mean, earlier I showed the decision tree, okay, with the levels. So here, those levels are recorded here, okay? And that will be used in determining the level to which you have to backtrack to non-chronological backtracking. Okay, and that's one. So there will be an arrow from there will be an arrow into, so the nodes here in this graph are the decisions, either explicit decisions which are denoted in green, which are made at the current level, which in this case is 3, or earlier levels, and all the non-colored ones are implied literals, the unit implied literals as a result of plugging these decisions in the clause. Okay, that's what. So, as a result of plugging X7, we're generating this implied literal in this clause C5. Okay, X7 generates this. Yeah. Similarly, the decision at X7 and the decision on X8 via clause C6 is forcing X6 to be a decision to be made on X6. Yeah. So all these are decisions, implied decisions that are made at level 3 as a result of the explicit decision that is made on X7. Okay. So this is what BCP does. And here I'm keeping track of the dependencies among the literals that are generated as a result of BCP and the clauses which generate them. That's all is being kept track of. Yeah.
Yep.
Okay. So then what? So after that, as a result of X6, an implied decision on X6, what will happen? And with let's see. So C4, for example, which had now has X6. Okay, this X6 as a result of X6 and X5 being this implied. So inside C4, X4, C4 becomes unit. Okay, forces the decision on X4. That's what is happening here. Okay, here. I think there is one difference in the in my animation, I think. Okay, so for example, here I'm already showing. No, yes, there is a decision on X6 and implied decision X6 and X5. So they become 0 here, and that generates. So C4 becomes unit, generating an implied decision for implied decision on X4. That's what is being kept track. Yeah. So now X4 gets plugged into C1, and X1 is already has been plugged into C1. So with X4 becoming 1, that makes yeah. So first I did C3. Okay. So there are two things that become literal as a result of the decision X4. So C3 becomes unit, and so does C1. Okay, and that dependency of the generation of X2, the cause of the unitary generation of X2 is being kept track. Okay, so that's what the implication of that does. Okay. So now with this, so is the so is implication graph generation clear?
Yes.
Yes, sir. Yeah.
Okay, yes, sir. Yeah. So now you can see that this what caused the conflict is very clear. Okay, so it also gives you a clear indication of how to block these cause of the conflict. The reason that there was a conflict, if you start from the conflict node, the reason was that there was a conflict eventually was there was a implied decision on X2 and X3 along with the explicit decision on X1 caused this one. So what that means is you cannot have X1 being 1, X2 being 1, and X3 being 0. Okay? Of course, some of these decisions were implied. Obviously, all the Y decisions were implied. That itself was a result of a decision on X7 level 3. So you could say, you cannot have a cause of the conflict is this set of decisions on X1, X2, and X3 being made here. Okay, or which itself was caused by X1 and X4. Correct? So that's also, so one way of preventing it is to say, X1, X2, and not of X3 cannot be true simultaneously. Or X1 and X4 cannot be true, because if they're true simultaneously, then the same thing happens. Okay? So in that sense, so similarly, it cannot be the case that X1, not X6, and not X5 can be simultaneously true. And the whole thing was caused by X1, X8, and not of X7. So that's what I meant, that there are various ways the same conflict can be prevented. So blocking any one of those set of decisions is actually good enough to block this particular conflict. Okay, so in other words, you can see that, and we chose one of them. Okay, so what we added, as you saw, was one of these things. You could now say X1 and X4 cannot be simultaneously true. Therefore, in order to block, a conflict clause is something which, when added, would prevent this conflict. Okay, so one possible thing is to say, not of X1 or not of X4. That is the negation of the decision that results in a conflict. is a possible conflict clause. Okay, and as I said, there are several ways to block this. Every and that's what we added. So now you can ask the question, why did I choose this one among all the other conflicts? Okay,
Because it is simplest, I guess.
Well, let's see. Okay, so but yes, there is that one. I'm going to skip all these things because these are something that you can go by. So, see, there is every cut on this implication graph, okay, that kind of splits this graph into two disjoint parts. One that has all the source, okay, which are the explicit decisions on one side, and the conflict node on the other side. Every such cut, okay, defines a possible conflict clause. Okay, conflict clause, as I just now said, is something that is implied by your original set of clauses, and it blocks the partial assignment that results, that causes this conflict. Okay, so this is one way of blocking. Okay, similarly, so this is another cut which separates. So once you cut it, these edges, you see, so that separates into two separate graphs, disjoint graphs with conflict on one side and the sources, the explicit decisions of this side. So then the nodes at the edge of this cut, okay, is, the negation of the disjunction of these things will be a conflict clause that can. There's also a cut that you can do here. Okay. Now, yes, like I guess it was Harsh or Amey, I don't know. So said the one nice thing is, I mean, you can add all of them, and if you want to. But since this X4 is kind of implied by these things, it doesn't make sense to add all of them. So one thing is, you can either, yes, it turns out that the one that we added also happened to be the shortest one, but it also has another property, okay, which is there is something called a unique implication point. Okay, see, this is a clause which has only one decision that is at the current level, and it is also a node from which every part from the explicit decision that is made at the current level passes through. For every part from the sink at the current level, that is X7 at 3, passes, X4 is something that every part passes through on its way from the sink, from the source of X1 to the conflict node, which means that this is somehow, it kind of captures the, all the earlier, decisions. Okay, such a clause in which has the, that decision at the current level, a unique implication point, okay, is of a special kind of a thing. Not only does it have only one decision, therefore it will be, among the short. That is one property it has. Okay, so this is X4 is certainly a unique implication point. X7, of course, the source, that is the decision that is made at the current level, is always going to be a unique implication point. So the two clauses, conflict clauses, which have unique implication points are X1, not of X1 and not of X4, that is one, or your negation of the original decision, not of X1, not of X8 or X7. Okay. Now the clause, the cut that is closer to the closer that the conflict design defined by a cut, clause that is closer to the conflict clause happens to be short usually. Okay, so more than being short is also important. But these clauses that have this unique implication point has the advantage of that being only a single literal, okay, at the current level, as opposed to, for example, this conflict clause, which with a cut here. I mean, this cut has x1, x4, this cut also. You can also have a cut like this that goes through C4, the way I'm moving my arrow. But that will give rise to a conflict clause which has x1, not of x1, or x6, or x5. Now, that is not, I'm claiming it's not as good because it has two literals. That conflict clause has two literals at that, two literals that whose decision, two literals which were implied at this level. Okay. Now, the advantage, such a clause which has a conflict clause which has only the unique implication is called an asserting clause. Okay, and the reason is. So the cut of the first unique implication point that gives the shortest conflict clause with a single literal at the current level. So when you add that, that has a very interesting property that when you add that and then you backtrack to a level, the decision, the decision on this x4 to block the conflict clause gets flipped automatically, okay? Because that's the only thing, because all the other decisions stay when you backtrack, okay? So when you say, suppose you add this clause and backtrack to, one of either level 1, 3, or 2, okay? Suppose you backtrack to x1, which is what we did in the non-chronological backtracking. As soon as you backtrack there, because the decision, as a result of the decision at level 1, because this has a unique implication point, automatically all the other, it becomes unit. Okay, so because all the earlier decisions will stay, and this gets automatically asserted, this particular unique implication point. Therefore, you don't need to make further decisions in order to in order to ensure that you would prevent that conflict. Okay, so that is so that is an important property. So a conflict clause that also happens to have contained the unique implication point as part of it is what is chosen, because that is an asserting clause. Okay. Sorry, this one is called an asserting clause. Okay, I don't know where I have that. And the reason that it is an asserting clause is because it has just a single literal, implied literal, or literal decision on which was made at the current level. And therefore, when you backtrack, the decision on that gets automatically flipped, preventing the other one. So that's why this, and you can get the shortest among them by choosing one that is closest, defined by the cut that is closest to the conflict. Okay, so so is that any questions there?
So we only need to keep one clause, or like keeping extra ones doesn't hurt.
No. Your question is, okay, so see, you can choose to that.
Let me rephrase the question again. Like, my question is like, is it redundant to keep other clauses? Like,
it's not redundant. Okay, because you can, just because you added this x. Not of x1, not of x4, okay? The one with the shortest and which has the unique implication point doesn't mean that you could not end up generating, for example, there could be another, for example, there could be other decisions that end up forcing x6 and not of x6 and not of x5. Okay, you could. So there may be other ways in which this could be forced. Okay, so there could be other clauses in which you have there might be other ways. Okay, this particular way might be prevented, but there might be other ways in which once again you will get not of x6 and not of x5. Okay. So the surest way, so then you will once again cause not of not of x4, and you can end up getting that could be a different kind of a conflict. So all it says, I mean, the surest way is to So answer to your question is no. So the surest, if you want to prevent all the clauses, then you have to add all of them. Okay, that is the what you can do is so here's what it is. You can add all conflict clauses that have unique implication points. Okay, that will ensure. Okay, so for example, here this is one x0, not of x0, not of x1 and not of x4, or you can even add this one. Okay, not of x1, not of x8, not of x7, or I'm sorry, not of x1 or not of x8 or x7. That will then force you. So you can either certainly adding all clauses that have unique implication points will prevent is one way of preventing all kinds of conflicts that happen as a result of this decision. Okay.
Okay.
Yeah. So you can add more number of clauses here to get that guarantee that you asked for. But the thing is, no, there's no guarantee. The only guarantee is you have to add every clauses. Okay. So the question that I'm raising is maybe you will get better guarantee if you added all conflict clauses that have unique implication points. Okay. Then you may avoid some redundancies. Even that doesn't mean that you will, something which is, caused by a completely different set of explicit decisions causing this thing might still be possible. Okay, because this is a partial implication graph, which is only analyzes the cause of the conflict as a result of this set of decisions. Okay, denoted in green. Maybe there are other clauses also in your original formula which may be such that those decisions also might result in x4 becoming 1. Okay, so there's no guarantee like at all that. Okay, that's what. Okay. That's
so I mean, the trick is to forget about to keep only the nice ones, or use some trick to keep the ones which you think are valuable.
That's correct. Yeah. So this one will certainly, yes. Okay. So that's right. So you could make. Yeah, so the SAT solvers use different things. Okay, so one strategy is it may add all conflict clauses with that contain unique implication points. Okay, and earlier SAT solvers, they added all conflict clauses before they realized that it was very soon was overwhelming, and a lot of those clauses never get used. Okay, a lot of those conflict clauses never get used, and that's why they based on that experience, most of them add only one conflict clause per which is the shortest, that is closest. That has a unique implication. An asserting clause that is the shortest, which means closest to the one. Some of them do use the strategy of adding all ones that have unique implication points. Okay.
Okay.
Yeah. Okay, so that is what I wanted to say. Now, there is a interesting thing. I think that is also described in the slide. I'm not going to go through today, but you can look at that. So the question is, so I've described it using this implication graph. The question is, do you have to generate this implication graph explicitly in order to derive the conflict clauses? One way is to construct the implication graph as I have shown here, compute the cuts and so on. That is not a very efficient way of doing it. Okay? You don't need to construct this implication graph explicitly at all. Okay? You can keep track of these chain in other ways, this dependency in other ways, and you can use resolution, okay? Resolution steps, working your way backwards from the conflict clause, doing a chain of resolutions on the clauses that are shown here, okay? To generate all the to enumerate all the conflict clauses, okay, from the one that is closest to the conflict clause all the way to the farthest, okay. And you could, you know, there's a way to do that as well, which is slightly more efficient than keeping the entire implication graph and doing the cut. And that is there. I mean, have slides, and it is also discussed in the book. That is interesting to review and learn. But maybe, you know, I will let you as an exercise to go through those slides, and you may revisit it, okay, later on. Okay, that's a more efficient way of generating these conflict clauses and also the asserting clauses. An asserting clause is one which has the unique implication point, okay, as a more efficient way of generating it. Okay. So with that, I want to move on. Okay. So any questions? Okay. Yeah, this is just a summary. Yeah. So as I said, yeah, what do SAT solvers do? So yeah, so I hope it's clear. It's very important that, you know, it's important that you understand the notion of an asserting clause. Just as a thing. Harsh, do you know, I mean, what is an asserting clause? I've already defined here. Okay. So it's one that contains UIP. Okay. What is the advantage of picking that which contains a UIP? Anybody? Devjit?
Wait. So you want the backtracking to not be conflicting with any of the. So
first of all, what is an asserting clause? That I have already defined. Okay,
yeah.
So maybe I'll rephrase my question. Okay, so among all the conflict clauses, the one
Yeah.
that has a unique implication point is an asserting clause. Okay, that is the definition.
Okay.
Now, you will. It turns out that with a unique implication point, it also will be a conflict clause that has only one literal. Okay. Exactly.
So here in this case, that would be X4.
In this case, it would be X4. So another asserting clause is one containing not of X1 or X8 and X7. So that also has only one literal at the.
Okay. That again should be X4, right?
That will be X7.
X7.
Yeah. So the advantage, I'll say again, of the reason that it is called an asserting clause is because when you add that and then you backtrack to the lowest, I mean, to the earliest level other than the current level among all the literals. See, that is the backtracking strategy that is used. I don't know, maybe that is that I had in there. That is the backtracking strategy. Anyway, I will, since I'm skipping slides, this is what happens. Okay, yeah. So the backtracking strategy, yeah, I think it becomes an asserting clause with the following backtracking strategy. So you add the asserting clause, okay, which has a single literal, and then you backtrack to the earliest level other than the current level among all the literals that appear, in that conflict clause other than the current level, okay? Which means, so X1 and so this clause has not of X1 or not of X4, right?
Yeah.
So you will backtrack to level 1.
Yeah.
If you used this a conflict clause with the unique implication point of which is now the source, then you would be backtracking to level 3, of course. Yeah.
Yeah.
That's the thing. So so when you do that, what will happen is, because when you backtrack, you will keep the decision even by keeping the decisions, the earlier decision with X1, because it immediately becomes a unit. Okay.
Yeah.
Because so then, I mean, it forces the right decision to prevent the conflict. Okay, you don't have to do any extra work, as opposed to, suppose if you added X, not of X1, X6 or X5, you don't know. You still have to. You don't know that you will have to make a decision of not of both of these. If you happen to make the same decision, you will end up hitting the same thing. Huh? So that's why. So,
but again, like so these are like implied decisions, right? So these are like not like, so if I fix X8 and X7, that's when I fix X6 and X5, right? So
that's right. So, but yeah, so what will happen is you may end up once again picking this one. Okay, you're making this choice, and then it can force you to make a bad decision on X5. Huh?
Yeah.
It can force that. No, because that asserting clause does not flip the decision. Okay, it does not flip the decision. Yeah. So you might end up hitting that anyway. Okay, if you added a non-asserting clause. If you added an asserting clause, and if you kept X1 and X8, it will force a decision on X7. You see, the right decision on X7, because the whole thing. Yeah. So if you added this, because X1 and X8 are kept, it will force. It will not even allow you to make the wrong decision on X7. Okay, and the same with with when you add X4. Okay. When you add not of X1 or not of X4. That's why it makes more sense to do non-chronological backtracking. You anyway ended up this, you might as well go there, okay, and get a good decision on X4, okay? And maybe your decision heuristics will not force X7 to be 0 again, okay? So that is, that is the whole. Yeah, so going back, the asserting clause has this important property that when you add and then you backtrack, it will automatically at least force the right decision on a literal that will prevent one source of the conflict. Yeah, that's why asserting clause is very important. Among all the conflict clauses, it picks either one that has either an asserting clause. If there are multiple, you can pick multiple ones as well. Okay. Like I've said here, pick only the first asserting clause, or some pick all asserting clauses, rarely all conflict clauses, because they turn out to be not that useful. Okay. Although they may prevent some conflicts. Okay. So if you okay. So with that, yeah, if you don't have any other questions, then I will. Any other questions? Okay, so let me now move to next thing. So how do we extend this? So the thing that I've not covered here, in addition to an efficient way using resolution to generate this thing, that I have information. Of course, Cyton. I mean, these are something that I want you to review, since they're the materials in the slides as well as in the supplement material, in the reading material. Cyton encoding, I certainly want you to go through. And then there is some decision heuristic called BSIDS, which is the standard decision heuristics that takes into account this conflict clauses as well, which is almost the standard one that is used in most modern solver. And that is something that I may get back to, but I have some slides. These are some things that I want you to review in the slides and with the help of the reading material for you to get familiarized with, so that because those are important things, and we may get back to this. So those are something that I have not covered. Okay. Let me now go to DPLLT right here. Even before that, I want to take the intro. Have that here. That picture, probably I don't. Okay. So that's okay. Have it here. Not sure. Which is the one that I wanted. Okay. Okay, so DPLLT. So, like you said, SMT, you can have any arbitrary propositional combinations where the atomic formulas are derived from the theory. For example, linear integer arithmetic. Yeah, so it can have. So the assumption here is that each of the theory solvers, they are able to handle the conjunctive fragment. Okay, like for example, if you take this formula here, this is a conjunction of atomic formulas drawn from linear real arithmetic. So an LP solver can handle this. Okay, as a matter of fact, SMT solvers use an LP solver as a solver for this. Okay, so LP solvers, and all the assumption here is that all theory solvers, we assume that they work on only the conjunctive fragments, which means they are able to decide conjunction of formulas. Okay, but SMT solvers, we want to be able to do decide on formulas of this kind. So, formulas in this kind have a Boolean structure at the top, but the atomic formulas have to, in order to have to obey the theory semantics. In other words, for this formula to be true, not only does it have to be a satisfying instance of this propositional structure, but the truth assignment to the atomic formula also have to obey the theory semantics. For example, if you view them, if I make a sign, obviously for this to be satisfiable, Z3 less than 0 has to be true, Z1 greater than this has to be true. And if I make this true, so as a propositional structure, just making this true and this true will will satisfy the propositional structure. But under the assumption Z3 is less than 0 and Z1 is greater than or equal to 0, it cannot be the case that Z1 minus Z3 can be less than 0. Therefore, that Boolean, the satisfying assignment that satisfies the Boolean structure will not be a satisfying assignment for this formula. Is that clear? So you will have to, your DPLL extension not only has to pick a truth assignment that satisfies the Boolean structure, that makes it satisfiable at the Boolean level, and but also your Boolean satisfying assignment has to preserve the theory constraints as well. Okay. Therefore, one way you could do that. So there is so your procedure SMT solver will have to combine, somehow combine the DPLL to take care of. The idea is to have an extension which will use some extension of DPLL and combines that with theory solvers. For now, I will assume like we have an LP solver, okay? At least for this, assuming is a way to extend DPLL such that it can talk to the theory solver and then do it. One way of doing it is to treat every atomic formula here as a propositional formula, okay? And you can get a satisfying assignment, for this, and then check if the satisfying assignment that makes the propositional structure true, if that preserves the theory semantics as well by invoking the theory solver. Okay, that is one way of doing it. Or another way is to integrate them more tightly. Okay, those are the two things that we will look at. Okay, and so.
Sir, one trivial way to handle OR would be to just do it one by one, I guess.
Yeah. So no. That you could do. So, see, you could do. Yeah. I mean, the idea with all this DPLL is, I mean, what is the idea of DPLL? I mean, for example, DPLL in DPLL2, you can do that, no? Huh?
Yes.
Yeah, but the whole idea of all these, I mean, the backtracking and all these heuristics that we talked about is to not do it, because if you do it one at a time, you will have to explore all possible assignments, no?
Yes.
Hmm?
Yes.
Yeah, so that will work as if you have only a few disjunctions in the thing. So even there, okay, very soon it'll explode. Okay, so DPLL, without all the bells and whistles that we so far discussed, is essentially doing that. Because it is so that's what so that is the thing. So what you're saying is a solution to the basic propositional structure, correct? Yeah. So the idea of using DPLL is so that you can yeah. So here is. Yeah, so what we are doing, this is the picture that I was trying to get at. Yeah. So the formulas are of this kind. So we'll assume the theory solvers are assumed to be able to do only the conjunctive fragment, because all decision procedures, for particular theories only usually work for the conjunctive fragment. Okay, but at least that is the assumption. Now, what DPLLT is a general way of combining all these theory decision procedures to be able to solve arbitrary propositional, decide proposition formulas that have any CNF. Okay, so the idea is to use DPLL, which is an efficient way of deciding on Boolean formulas, and then consult, okay, query these theory solvers as and when you require. Okay, so that is the idea. So as if you view these as black boxes, one way to do is to only keep the propositional structure and then get a propositional assignment and then check if that is the thing. Now, what you're saying is how you could get the propositional satisfying assignment to the prepositional structure. Okay, that of course is, you could say, oh, you can split the disjunctions. You can split the disjunctions in all possible ways. But for that, you have DPLL anyway, right? To do it more efficiently. So we want to use, the SAT solver, which is DPLL with all the heuristics, but yet integrate that with the theory solvers to ensure that whatever satisfying assignment you get out of the DPLL also satisfies the theory semantics. How do you do that? What is an architecture that can do it very efficiently for any theory solvers or combinations of theory solvers is what SMT solvers do. So by extending DPLL to be able to handle any theory for which you have a decision procedure for a conjunctive fragment. How can you do that efficiently is what we're talking about. Okay, so this is the basic structures. What you can do is you can kind of get replace all the atomic symbols. That's what I mentioned. I mean, atomic formulas in your original formula by distinct propositional variables, and then run DPLL on it. That will give a satisfying assignment. Of course, that will preserve the proposition structure. There's no guarantee that it will preserve that will give a satisfying assignment. And then you can then send it to the theory solvers, which we haven't discussed how to combine them, but let's suppose that they are combined into a single procedure. Okay, and then you can check if that satisfies the semantics, and then you get a SAT. If that unsat, then you have to use another search for another satisfying assignment. Okay, so this is one way to do. Okay, this is what I call as an offline version, where the DPLL is the original DPLL. With bells and whistles, CDCL, or rather DPLL, let me say CDCL. Okay, but it uses the theory solvers as black boxes. Or a better approach is a little bit more tightly integrated ones. Okay, that integrates. It talks to the theory solver at a. It kind of makes. And that, I'm sorry, this is slightly different. So here, there is an online version which kind of, integrates the solver into the DPLL procedure itself. That's what gives you DPLLT, and why that is more efficient than the black box offline approach is something I will explain. Okay. So here is what you do is, of course, you assume that your SMT formula is converted into a CNF form. And then what you do is, this is theory to Boolean. Okay, you just replace every atomic formula in that, atomic predicate in that, by a propositional variable. Okay. That is T to B computes the Boolean skeleton of that. Okay, and then you run CDCL as before. If that is unsat, of course, your original formula is unsat as well. Correct? Because any satisfying assignment of a SMT formula will have to satisfy both. It satisfies propositionally as well as it has to satisfy the thing. So if the propositional structure itself is unsatisfiable, then it is unsat. Or you resolve, then if it is satisfiable, then you pass the satisfying assignment by substituting all its original atomic formulas. So because any satisfying assignment that you get will be a cube, correct? So that is inside the conjunctive fragment of your solver. So you can invoke the solver on that, okay, after you replace the propositional variable with their original atomic formula, and then you invoke the solver on that. If that gives satisfied, then you return sat. If not, then you block that the satisfying assignment which did not work for you, and then you rerun this thing. Okay, so that is the idea. So whenever this happens, the solver says, no, this doesn't, your satisfying assignment is not good enough for me, then it means that is what, when there is, we say that there is a theory conflict. Okay, so the satisfying assignment, which is a Boolean satisfying assignment, when expanded, will not work for you. So that is a theory conflict. So then you will block that propositional assignment and then go back. So this is the offline approach. Okay.
Sir, do you have like a more concrete example?
Yeah, I do. Okay.
Yeah. Oh, okay.
Okay. So what is this? So consider this formula. Okay. This is a formula in say linear integer arithmetic. It's a formula in CNF. So the atomic formulas are these. So the Boolean abstraction of T to B is exactly this. So every atomic proposition in the original formula I replace by a distinct propositional variable. That's what this thing does. Okay. So if it's a theory atom, then it picks a new, it replaces that with a new propositional variable. And if it is already a propositional variable, then it keeps it. Okay. And otherwise, it just goes down the hierarchy. So this is exactly what what it does. This is the recursive definition for obtaining the Boolean abstraction of an SMT form. So this just throws away the theory information from the thing. So it reduces it to a purely propositional formula. Okay. Now is it clear? So that at least the conversion.
Yes.
And B to T, that is saying Boolean to theory, is the inverse of that. So given this formula, it will get you back. It replaces the proposition. I mean, it gets you back to theory. That's what T to B and B to T do. So here is an example. Let me go to the example itself first and then come back to that slide. So what do? So first you get the propositional abstraction of the original formula. Then you get a satisfying assignment. This is a possible satisfying assignment. Okay. Then you check if what am I doing? Yeah. Then you check if this assignment satisfies the theory semantics. Will it?
No, I guess.
Why you
Yes.
guess? Because how can B1, B2, and B3 all be true? I mean, because x is equal to 1, x is equal to 2, and x is equal to 3 simultaneously can't be true, right?
Yes, but if you have a different theory, then it won't be true.
No. But here I'm assuming that we are working with this. This theory. Here I'm assuming that I'm working in a linear integer arithmetic SMT theory. Okay, this is linear.
Then it can't be true.
Yeah. So the idea here is, of course, that's what SMT is. When I give a theory, if it's a theory in which 1, 2, 3 will mean same thing, then it's okay. Okay. Why am I getting this question? Okay. Yeah, I'm assuming. SMT solvers, they work with specific theories only. Okay, so you have to instantiate. Yeah, You may be able to satisfy that in some theory that you have constructed in your own imagination, okay? But here we are assuming that it is integer theory. Therefore, so what you have to do is that will not work, and now you block that. So here, so that can be checked by refining your propositional abstraction by applying B to T and then sending it off to a theory solver. Here, the theory solver will be, integer linear programming, simplex algorithm. Okay, that can, you don't even, in this case, you don't even need that complex a thing. So you know that x is equal to 1, that is not possible. So certainly, an LP will return this to be false. Correct. Okay. So then you block it. You can do this at a time. Okay. Then you block it. Then you get another one. So here, this is never. This is unsat. Correct. Is this formula satisfiable? No.
No.
Yeah. So in order to get that unsat, you will have to try. So this black box offline approach is not very efficient. It's also not very, you will have to enumerate, okay? Of course, it has the advantage of using the solver and the DPLL as black boxes and just interfacing them at that thing. So that's why more integrated approach will be better. So what is that integrated approach? See, there are several things that's happening here. One is that you are getting the full assignment to your proposition structure and checking it. Okay. Often, it may be better, maybe even a partial assignment may be, may not be good enough. Okay, may not satisfy the thing. Therefore, instead of calling this theory solver at the very end, okay, it may be better to, so here you're calling only after you get full assignment. Maybe integrating the theory solver into the DPLL process, wherein even while you're generating the smaller assignments, that is one. More importantly, okay, is there a better way to do? So, no, forget about it. So I haven't introduced unsat core. So here it is. The other thing is, suppose after your first thing, you're able to query. First thing is, why not consult your theory solver? Don't for a moment ignore the unsat core in here. So assume that you had just the previous thing. So first thing is you can consult your theory solver after every assignment. So for example, if you know that B1 is true, theory solver, you can say if x is equal to 1, then you know that x is equal to 2 cannot be true. If somehow you could consult your solver and then derive certain facts from the theory solver, then maybe you can add that, okay? So, since you made a decision on B1, you could say, since if x is equal to 1, can I even have x is equal to 2? So you may be able to, see if your theory solvers can be invoked instead of just checking, giving yes or no. So is that, what are the other literals that can be either true or not true? Then maybe you can use that with the partial information, partial assignment that you get, and then you can add that. So since if you know that x is equal to 1, x is equal to 2 can never be true. Therefore, so then you may get better things. So after that, you get another assignment. Then with B1, you also know that if B1 is true, B3 cannot be true as well. So that is what as where you consult your theory solver, even while you get on your partial Boolean assignments, and do not only check if the partial assignments will obey the theory semantics, as well as trying to get some theory propagation that maybe you will get some as a result of the partial decision if certain other facts about your theory literals can be deduced and then used in your DPL. Then you don't have to wait till you get a full assignment to be able to consult the thing. So basically what DPLLT does is it does a tighter integration of the DPLL procedure. Okay? And we'll see that the theory solver is somewhat integrated into the BCP process itself, the Boolean constraint propagation box. Okay, and we accomplish remove these two disadvantages through that tighter integration. Okay.
Sir, isn't the main problem with theory of integers are such clauses where x is greater than y and x is less than 1 or something like that?
Yeah. You broke up slightly.
Yeah. So what I'm saying.
Repeat.
Yeah. Isn't that the main concern? I mean, I get all these. Okay, so you're basically trying to make this procedure faster, right? Now.
Correct. Yes.
Oh, okay. I get your point.
That's right. Yes. So can I? Yes, in two ways. One is by invoking by consulting the solver even on partial assignments. Okay.
Yeah.
So waiting till full assignment. So because if the partial assignment itself, doesn't satisfy theory constraints, then why bother? Okay, till generate full assignment. That is one. Number two, based on the partial assignments, can I now consult the solver to get some new facts? Okay. So, for example, if even in equality, if x is greater than 1, if x is greater than if x is equal to y and y is equal to z, and then some other, and you have another atomic thing saying x is not equal to y, x is not equal to z. Obviously, that's not possible. So equality preserves transitivity.
Mm-hmm.
The theory can say, now you've already chosen x is equal to y and y is equal to z, and therefore you can derive that y is equal to z, and then pass it on at the Boolean level to DCLO. Therefore, you can prevent, you can block certain decisions, much like what preventing these theory conflicts. Okay, ahead of time. Yeah, that is the idea. Yeah, just like you learned clauses, conflict clauses to prevent future conflicts, Boolean conflicts. Here, why not consult your theory solver? Okay, to get some theory, use it to get some theory deductions, and then deduce certain new facts, which will then be used in your DPL. Okay, based on the partial assignment. Those are the two improvements that are done by going from offline to online. Yeah.
Yeah. Okay. Yeah.
So here is the online version. Okay. So I'm going to also bring in. Yeah, I'm going to go till 5 o'clock today. Okay. Since I'm going to give you. Unless you have tomorrow is Diwali, I know. But if you have some plans, I can stop here. Okay, so I'm okay with it. So,
sir, I actually have a class at 5 o'clock. So maybe just 5 minutes before.
You normally have a class at 4:45. I mean, at 5 o'clock. Is it? Or what time?
No, on Wednesday I have at 5 o'clock. I have a class.
So okay. Then I'll go. Oh, that's at 5 o'clock. So I'm going to stop at 5 o'clock. But then no, it's not fair. So I'll stop. I'll only take 10 minutes. I'll stop at 5 minutes to 5. Is that fine?
Yeah, sure. Yes.
Unless you want to take a longer break, then I can stop.
No, that's fine. 5 minutes.
Okay. Yeah, I'll take 10 minutes. Yeah. Is the one that I have. So I want to give this, show this side by side. Yeah, this is my CDCL, okay? Start from here while true. So what you have is, yeah, it's basically follows the same CDCL structure, okay? What we do is, you see, so compare the while loop here and the while loop here, that's all, okay? So instead, the decide is extended to making decisions in a theory-aware way, okay? So earlier, the CDCL had to make only Boolean decisions. Here, you will see that you will have in a theory-aware way, okay? But that is one. But we have a more generalized version of BCP, okay, which is called T-deduce. Okay? It does the normal BCP, but it also invokes the theory solvers, consults the theory solver as it does Boolean constraint propagation. Okay? So that it can do the two, it can remove the two drawbacks that I mentioned earlier. Okay? It can work with partial assignments and also deduce, use solver to deduce certain true formulas in the theory as it does Boolean constraint propagation. And similarly, the analyze conflict and T backtrack are also slightly modified. Okay. What I will do is, now I'm going to stop this. Yeah. So you can have a pre-processing step, okay? So, but let's just ignore the pre-processing. I mean, maybe most SMT solvers do certain pre-processing at the top level before they do it. But let's assume, and I'm not going to talk about those pre-processing thing. Okay. So, like I said, this is analogous to decide CDCL. It selects a new unassigned literal. Okay. I mean, first, of course, it does. It first starts with generating the Boolean abstraction, okay? And assume mu, which is the assignment to the literals, starts with empty, like earlier. So, T, then it selects an assign. It may consider some semantics of the literals in T. And T deduce does a lot more interesting stuff, okay? Yeah, so what it does is it uses it does the usual BCP, okay, until if it propositionally violates thing, then it generates a conflict as before. But if it propositionally satisfies, it is able to come up with a satisfying assignment, then it invokes the T solver. And it returns SAT if the T solver does. Okay? Otherwise, it returns conflict. But it also, even with partial assignments, even if neither of these two things holds, okay? Even with partial assignments, it may, that is, if with partial assignments, you neither get conflict, you don't get a conflict, nor you get a fully satisfying assignment. That happens when you have unresolved clauses in your abstracted formula. Then also, even on those partial assignments, this is the case when it invokes the T solver on partial assignment. Okay, after refining the that assignment. Okay. Because the partial assignment will only have assignment to the propositional variables, which were used in place of the atomic solvers. Okay, and then you can have you can do B to T. Okay, on that it invokes. Now there it can do, if that returns unsat, you can say, look, this is not no longer this is not this doesn't work, this partial assignment. Therefore, you have to look. So it can then give an early conflict. That's why this is called early pruning. You're pruning even the partial assignments which do satisfy well, the partial assignments which may themselves not satisfy the theory semantics, and therefore you give an early warning, early conflict, okay, if there is unset. So therefore, even those partial assignments are pruned away early, okay. And additionally, it may do some theory propagation by actually getting new facts. Okay, that's what that's what it does. Okay, so analyze conflict. It just does something very similar, but here you can get two kinds of conflict clauses. Okay, the original kind of conflict clause, which are purely propositional in nature, but you can also get conflict clause due to theory failures, and therefore you get these mixed conflict clauses. Okay, so the analysis will have to take both these two kinds of conflict clauses from arising. The backtracking works pretty much the same way. Okay, so I think I'm going to stop here. So because I think I only have 5 minutes. It's all around less than 5 minutes. So I'll take, so we have only 2-3 minutes before we will have to leave. So I will start with the, I'm not sure if I'll be able to, let me see. I mean, I will do as much as I can. So we are meeting on Friday, okay? So that is an extra class that I plan to have. Is that okay with you? Or you have any other engagement?
So can it be like early in the morning? Then?
Yeah, I mean, which one works for you? I'm okay with the morning also.
Yeah, because I have to travel a bit for this thing called Hypota.
Okay, so what time in the morning?
10:30 works for me. Everyone will be
This is who?
Devji.
Devji. Okay,
Yeah.
10:30. Will 10:30 work for?
Yeah, it works for me. Yeah.
Okay, so we'll. That was Harsh, I guess. No, Ameya. So how
Yeah,
about
that
So
Harsh?
it works for me too.
Okay, so then 10:30 we will meet. Yeah, and I appreciate your consideration. Yeah.
Thank you, sir.
Okay, thank you, sir.
Thank you, sir.
Okay, thank you.